Hello, welcome to my talk. My name is Lopez-Diaz, and it is my pleasure to present this work that was done in collaboration with Rocío Llanes and Miguel Rodríguez Rosa at the University of Salamanca in Spain. The motivation for this work is that we wanted to study what happens when we put a domain wall inside a thermal gradient in an antiferromagnetic material. But let's have a look first what happens in ferromagnets and ferrimagnets, because here we have more experimental evidence. I just highlighted here some of the works that have been done regarding this matter. And for example, here this is in permalloy and this is also in permalloy, but the origin of the thermal gradient is different. Here is the heat with a laser spot, whereas here the thermal gradient is due to the Joule heating when passing the current through the nanowire. This one is for perpendicularly magnetized cobalt iron boron, and again the heating is with a laser spot. And here is for YIG, and in this case the heating is, they use a Peltier cooler for the heating, for the thermal gradient. In any case, different systems, different ways to create the thermal gradient, different materials, but in general, the observation is that the domain walls move towards the hot region. In all cases, this seems to be a very general effect. Can we understand this from a theoretical point of view? The answer is yes. There are different models. I'm just going to highlight two of them without going into the details, just describe the basic ideas behind them. The first one is thermodynamic in nature. And it basically says that here in the hot region, because there is more disorder, fluctuations are higher, the effective exchange field is smaller than in the cold region. As a consequence of this imbalance in the effective exchange field, there is a force that pushes the domain wall towards the hot region. This is usually called a thermodynamic torque or third thermodynamic force or entropic force, because it can be shown that this is equivalent to the domain wall moving towards minimum energy, the system having minimum energy or maximum entropy. And then there is a second model that is magnonic in nature. It's a completely different approach. It considers that when we have a thermal gradient, we have a thermally excited spin current. In other words, magnons are flowing from the hot to the cold region. And if you take a magnon, this is a schematic representation of a magnon. This is the magnetic moment of the magnon, which is opposite to the magnetization. When it travels and crosses the domain wall, its magnetic moment flips by 180 degrees, which means that the change in the magnetic moment of the magnon, like this. So by conservation of angular momentum, there has to be an opposite change in the magnetic moment absorbed by the domain wall, and this absorption of magnetic moment is what pushes the domain wall towards the hot region. So both models explain the experimental observation, and to some extent they are complementary to each other. Now, if we go to antiferromagnets, the evidence for the motion of a domain wall in a thermal gradient is very recent. As far as we know, this is the only evidence, and the paper came out this year. In this case, it's chromium oxide, an insulated antiferromagnet, and the heating, local heating, is also with a laser. So by focusing the laser on a laser spot on a region, they observed that the domain wall tends to approach this laser spot. And if they move along the laser spot, that they are able to drag the domain wall along. So this again is an observation consistent with the domain walls moving towards the hot region. And this can be also explained theoretically if we use the thermodynamic model, the first of the models that I mentioned before. This was done in these two publications here from Uli Novak's group, and they showed that the domain wall moves towards the hot region as a consequence of basically the same principle than in ferromagnets. In particular, the domain wall moves to the hot region to minimize the internal energy of the system, maximize the entropy. This is what happens for a ferromagnet, and this is for an antiferromagnet at successive time instants. And as you can see, the domain wall moves to the right. In this case, this is the hot region. It's on the right. And for the antiferromagnet, it moves faster because, as we know, domain walls move faster in antiferromagnets. So they were even able to derive an expression for the domain wall velocity driven by this thermal gradient. This velocity is proportional to the thermal gradient, and it's also proportional to this factor over here, where A is the exchange constant, and this has to do with the fact that, as I mentioned before, the force driving the domain wall is related to the temperature dependence of the effective exchange field. So this is the general situation where we jumped in. We wanted to jump in and investigate further, adding a new ingredient that had not been taken into account so far, that is the external field. So to do that, we use a very simple model for the antiferromagnet with two identical sublattices. It is perfectly compensated. It's in a cubic array, and we take this elongated element. A is the lattice constant. Here you can see the dimensions, and we put a domain wall in the middle and a thermal gradient from where temperature is decreasing from left to right. We consider a very simple Hamiltonian, taking into account only exchange, anisotropy, and Zeeman term. And for the anisotropy, we consider biaxial anisotropy. This is the main uniaxial anisotropy, where x is the global easy axis, and then this is a secondary uniaxial anisotropy, where in the YZ plane, y is the easy axis, z is the hard axis. We integrate the Landau-Lifshitz-Gilbert equation, including noise. This thermal field is basically noise that is taken into account the usual way with the correct statistical properties. And we choose the following material parameter values for the lattice constant, atomic magnetic moment, exchange constant. The anisotropy, we take a pretty large value for practical purposes so that the domain wall is narrow and the computational study is not so time consuming. And the secondary axis is secondary anisotropy is 10 times smaller, and alpha 10 to the minus 2. Okay, so before showing what happens to the domain wall inside the thermal gradient, I would like to highlight a couple of things to keep in mind for the results that will be shown later. The first of all is that I forgot to mention, but the applied field is the field is applied along the easy axis. And when you apply the field along the easy axis, at some point you get the spin flop transition. In other words, the Néel order parameter orients perpendicular to the easy axis. We are going to consider applied field only in this region, below the spin flop transition. And secondly, I want to point out that in antiferromagnets, unlike in ferromagnets, we have two magnonic branches when the field is applied along the easy axis, below the spin flop transition. So at zero field, the two branches are degenerate, but as we start increasing the field, the two bands split and the gap between them opens. And it's important to point out that at zero field, for a field different from zero, these magnonic currents carry angular momentum, because in each one of these modes the two sublattices are not excited with the same amplitude, which means that the magnons propagating in the system carry angular momentum. I forgot to mention something that is important when I was discussing this result, is that the thermodynamic model in tropic torque, we can explain that the domain walls move towards the hot region, but this is not, it is not possible to explain this using the magnonic model, because in the absence of an applied field, magnonic currents in antiferromagnets do not carry angular momentum. So it wouldn't be possible to explain this effect using the second model that I described. Okay. So once I have pointed out these two aspects, let's see what happens when we put the domain wall inside the thermal gradient in the presence of an external applied field. From now on, I will use this lowercase b for the external field, which is the external field in Tesla divided by the spin flop value. So b is going to be between 0 and 1, always smaller than 1. And time, I'm going to use this measure in units of tau for convenience, but this is not so relevant. Just keep in mind that the results I'm going to show, the typical length scale is a picosecond regime. It's pretty fast. Okay, so here we are plotting the Néel vector Cartesian components as a function of time for an applied field 0 and for an applied field close to the spin flop. This is a large field, this is a 0 field. So we can see that for 0 field, the domain wall moves to the left, that is to the hot region. For a large field, it moves to the right, that is to the cold region. And this is confirmed in this figure on the right, where we plot the Néel vector component along the z-axis for the same time, instant of time, for different applied fields. So this transition in the Cartesian component of the Néel vector tells us where the domain wall is at that particular instant of time. And we can see that for 0 field, the domain wall is further to the left. And as we keep increasing the field, the domain wall moves less and less. For 0.6, it hardly moves. And for 0.8, it moves, but it moves in the opposite direction, towards the right. And this is indicating that by introducing an external field, a force appears on the domain wall that pushes it to the right. And here at the bottom, we are plotting not the Néel vector, but the net magnetization along the z-axis to point out that it is not 0, particularly it's not 0 at the domain wall. This is where the domain wall is for b equal 0.8, highest field. And you can see at the profile of mx that mx is not 0 and that there is a peak here which is around above 0.1, which means it's a sizable net magnetization component, even though we are in an antiferromagnet. As we decrease the field, this net magnetic moment decreases, and for low fields, at 0 field, it's the domain wall position is hidden here. We cannot see because it's hidden in this noisy region. But anyway, let's keep in mind that if the applied field is large, there is a net magnetic moment inside the domain wall. Okay, so we can also monitor the position of the domain wall in time to obtain the trajectory of the domain wall. And this is shown here for different applied fields. And as we can see, the trajectory is irregular, but there is a clear drift in the trajectory, and this is field dependent. So it makes sense to compute the average velocity. And to get statistically good results, we do several realizations and obtain the average velocity. And if I remember correctly, this is for 5 realizations, and this is the average velocity as a function of the applied field for both positive and negative applied field. And as you can see, we obtain basically the same behavior in both cases. We have a negative velocity for zero applied field, means that the wall moves towards the hot region, and then a gradual shift towards positive velocity, that is to the cold region, as we increase the field. So around 0.5 or 0.6, the force pushing the domain wall towards the hot region is overcome, and we reverse the direction of a domain wall motion. So again, this is indicating that there is a force, that the applied field introduces a force in the domain wall that pushes it towards the cold region. How strong or how robust is this effect? Is this by coincidence, or is it more like a general effect? So to figure that out, we tried with different values of the thermal gradient. We tried removing the secondary anisotropy. It's considered pure uniaxial anisotropy, and it turns out the same result holds. We tried also, I mentioned before that we tried with high anisotropy for practical purposes, but if we consider a low anisotropy antiferromagnet, we did some trial cases, and the same physics, the same result remains. So this is indicating that this is a quite general effect. Moreover, if we plot the velocity, we divide it by the strength of the thermal gradient, we see that all the data tend to fall within the same curve. And this is indicating that the force that we have identified is proportional to the thermal gradient, which of course it makes sense. And we use that to fit or to characterize this domain wall velocity using this formula. It's proportional to the thermal gradient, as I explained, and we have this. This reflects the part that is independent of the applied field, and the dependence on the applied field, that the new effect that we are trying to understand and characterize, is here. So if we fit this data to this formula, these are the values that we obtain. So for A, this coefficient, we obtain this value, and this is close to the theoretical value that you obtain if you from the thermodynamic model that does not include the effect of the external field, the one from Uli Novak's group that you can find in this publication here. We obtained 1.5310 to the minus 6, which is close to the value that we obtained here. And then the new part, which the part that deals with the dependence on the applied field, is here. It goes with a minus sign, and we get an n 1.25, meaning that the best fit is not for a linear dependence, but 1.25 dependence, and the value for the coefficient C is given by this. Now, once that we have seen that this effect is robust, and that we have characterized it, we want to understand what is the origin of this force. Why, when we apply a field, then this force appears on the domain wall, pushing it towards the right. So we thought that it had to do with the fact that I mentioned before, that when you apply a field, the net magnetization inside the domain wall is not zero, but the domain wall has a profile like this, with a net magnetization that depends linearly on the applied field. So the internal structure of the domain wall changes, and that we guessed that was the key issue to understand what is going on. To see it more clearly, this would be the profile of the domain wall in the absence of an applied field. So we have perfectly antiferromagnetic order. If we apply the field along the easy axis towards the right, there's a small tilting inside the domain wall, not in the domains, but inside the domain wall, so that a net magnetic moment develops. And for a large field, that this net magnetic moment is not small, is around 0.1. It means that the antiferromagnetic order is significantly broken inside the domain wall. And we can understand this from a qualitative point of view if we consider that the spins inside the domain wall are perpendicular to the easy axis. So they are, you could say, spin flopped, and the susceptibility to the applied field is much higher when it's perpendicular to the easy axis than in the domains where it is parallel to the easy axis and the susceptibility is essentially zero. Moreover, if we plot this velocity divided by the thermal gradient as a function of the net magnetic moment inside the domain wall, this is magnetic moment per unit area inside the domain wall, and this is created by the external field, of course, but instead of plotting as a function of the applied field, as before we plot it as a function of the net magnetic moment, we get a nice linear behavior, which is somehow indicating that this change in the internal structure of the domain wall is key to understand the effect that we have identified. And secondly, we also thought that the origin of this effect was magnonic, so that it is what happens is that this magnetic moment inside the domain wall changes the way that the domain wall interacts with the thermally excited magnets that travel through the domain wall. And a good indication of this is that if we measure the dependence of this velocity as a function of the applied field with respect to the damping parameter, we see that as we decrease the damping parameter, the effect increases, which is a good indication that the effect is magnonic. So to investigate that more clearly, in this second part, we put aside the thermal gradient for a moment, and what we did was to excite monochromatic spin waves on the left of the sample. They propagate, interact with the domain wall, and we're going to see what is going to the result of that interaction, what happens. So the spin waves are excited by imposing an oscillation on the left part of this fashion, a pure sinusoidal oscillation. We are going to see here how the domain wall interacts with this spin waves, these magnons traveling from left to right. Here I'm plotting for a large field, 0.8, and here for a small field, 0.2. The frequency is the same in both cases, and we are plotting the Cartesian components of the nail vector on the top and the magnetization along the easy axis. Sorry, the perpendicular component of the magnetization along the z-axis for the two sublattices to see the spin wave propagating. So let's see first, for a small field, how the spin waves reach the domain wall and they pass through without significant modification. And as a consequence of this, the domain wall moves slightly to the left, but this can be hardly seen because the displacement is very small. Whereas here, for a much higher field, we can see how the spin waves are reflected by the domain wall pretty efficiently. As a consequence of that, the domain wall moves to the right. So this is indicating that when we increase the applied field, the magnetic moment inside the domain wall creates a barrier for the magnets, so that magnets are reflected, and when they are reflected, they push the domain wall along the magnon flow. They transfer linear momentum to the domain wall that moves towards the right. And we think this is the origin of the effect that we have identified in the thermal gradient. And this is confirmed if we carry out a systematic frequency analysis as a function of not only the applied field, but exciting magnons, spin waves of different frequencies. And what we do is we monitor not only the domain wall displacement for each value of the frequency and the applied field, but also the reflected power. And we are able to estimate that by comparing the intensity of the spin waves with and without the domain wall in the region after the domain wall. Measuring that, we can extract the reflected power and plot it as a function of frequency and field. And as you can see here, there's a very strong correlation between domain wall displacement and reflected power, which is confirming our guess, namely that the domain wall, when the field is applied, because of the net magnetic moment inside it, it increases its reflectivity, and it reflects the spin waves that, when reflected, transfer linear momentum to the domain wall and push them towards the right along the magnum flow. Note also that there is a strong frequency dependence. You can see that the maximum in the reflected power and in the displacement is slightly above the threshold for this lower branch. So in other words, the domain wall reflectivity and domain wall displacement increase as we increase the applied field, and for a given applied field, it depends on the frequency. The maximum reflectivity, the maximum domain wall displacement occurs slightly above the threshold of the lower branch. So our main conclusion is that it's mainly these magnons here above the lower branch that contribute to pushing the domain wall towards the right. In the case of the thermal gradient, we believe this would also be the case, because the low frequency magnons are more populated because they have less energy. So we also, although we have not carried out an analysis, frequency analysis in the case of the thermal gradient, we also believe that it's mostly these low frequency magnons in this region that are responsible for the force appear, on the domain wall that pushes towards the cold region. And finally, we also note that there's a strong correlation, but if you notice the domain wall displacement is a little bit shifted up in frequency with respect to the reflected power. And we believe that this is because for a reflected magnon, the higher the frequency, the higher the linear momentum. Therefore, this higher linear momentum transferred to the domain wall, and consequently the domain wall displacement is larger. This is the reason why we think it is shifted up in frequency with respect to the reflected power. Okay, so let me go to my conclusions. We have identified a new force when we apply a field along the easy axis in an antiferromagnet that pushes the domain wall towards the cold region. This force is proportional to the magnetic field and the thermal gradient, and for sufficiently large applied field, it is able to overcome the entropic force and consequently reverse the direction of motion of the domain wall, which now is going to move towards the cold region. The origin of this force is due to the increase in the domain wall reflectivity with the applied field, so that magnons, when they are reflected, they transfer linear momentum to the domain wall and push it along the thermal magnonic current. And this increase in the reflectivity, we think it is linked to the sizable increase of the field-induced net magnetic moment inside the domain wall. So since antiferromagnetic order is significantly broken inside the domain wall acts as an energy barrier for magnons that are therefore reflected. Finally, let me point out that we think this is a pretty robust effect pretty general, then it should be observable in most insulating antiferromagnet materials. So with that, I thank you for your attention. I'm ready to answer all the questions you might have.